Great. Well, thank you, Kevin. And also thank you, Meg. Um, uh, and good evening, everyone. I suppose it's evening. Days are getting longer. It doesn't quite feel like evening yet, but and bear with me while I share my screen. All right. And can I see a thumbs up if the screen is shared? Great. Thank you. Okay. Well, so what I'd like to do for the next few minutes is share with you climate trends in Maine, Vermont, and broader New England region. And I'd like to share temperature and precipitation trends. I'll note some of the heavy precipitation events that we've seen recently, but also I thought it'd be interesting to explore the growing season and how that ties in, and then uh, wrap it up with maybe covering a few resources. And I also wanted to mention, just give you a little bit of background on who I am. Um, I am My position is joint between the Climate Change Institute at the University of Maine as well as Cooperative Extension. And my two roles are research, and that's through CCI, and through Extension. My primary role is as the Maine State climatologist, in which I provide climate services. That's the production of information, data products, providing data to stakeholders in the state to facilitate decision making. I'd like to acknowledge my colleague Leslie Ann Bigney-Giroux in Vermont, who's the Vermont State climatologist as well. I work with Leslie Ann closely on a number of projects. And so the overall outline, go over some key points at first, then we'll step through some data for temperature, precipitation, highlight some weather extremes, including some notable extreme events that have impacted the entire region, including Vermont and Maine, and then some aspects of the growing season, especially where the growing season is not too far away now, and we'll be looking out for when the last frost happens and so on. And then we'll, if there's time, step through some resources. First, I thought it'd be helpful to just put some of the highlights right up front. When we think of the changing climate in this region, there's been warming across all seasons, especially in winter. And then I also, as you can see on the slide, I put in parentheses in fall. And by fall, I also include late summer. August, many people who've lived in this region a long time have noticed that August seems a lot warmer and hotter and more humid, and September as well. There's been a lot of warming in those 2 months. There's an overall increase across this region in annual precipitation. Um, and the largest increases tend to be in summer, and you'll see some of those data. And changes in weather patterns are associated with the changing climate, and they've tended to produce more extreme patterns that produce heavy precipitation events, as well as there's an increased likelihood of heat waves as well as cold waves in some situation. That relates to how the overall circulation of the jet stream is changing. And then the growing season, it's lengthening overall, and there's a greater accumulation of heat, more growing degree days. But the first and last frosts, that's very much event driven, and there are recent notable surprises, including the May 18 frost event that had a big impact in Vermont in particular. A few more highlights. If we break this down into winter warming on agriculture in general, impacts chill hour deficiency, or produces chill hour deficiencies. Warming also can produce winter injury from large temperature swings, and then fall, spring. And as well as we've all been experiencing, not so much this winter, but in definitely last winter and recent winters, midwinter rain events, and that produce runoff and erosion and overall unreliable snowpack. And then warming can facilitate an influx of new pests and invasive species. And that's also, of course, true of warming in the summer. Um, that can help facilitate the northward influx. And then warming can also facilitate crop yield loss or quality changes due to heat stress, and just overall greater pressure for irrigation. Although we have seen very recently that even in a warm year, we can get a lot of rain, and 2023 is an example of that, whereas in 2020 was a very dry year. And so part of the extremes that we need to manage, of course, are not just weather events that can bring extremes, but also month-long or seasonal scale extremes that we all need to be able to manage. Now, with the changing climate, there are many challenges and many obstacles to overcome. There are some benefits, in terms of with a longer growing season, um, and with more growing degree days, there are opportunities for new crops that can be grown and different varieties. And so just to add that there are at least some positive aspects of this, even though there tend to be more challenges than benefits. And this particular slide here, I put together for Maine, but it broadly applies to all of New England. In terms of the overall temperature change, over in the top right part of the slide here, these are annual mean temperature values from 1895 to, well, this ends in 2023. I still need to update for 2024, my apologies. But the slide shows the annual variability in red, and then this dashed line is the linear trend across the entire period. And then this bold line in black is the 5-year running mean. So in one figure, we can see the year-to-year variation, we can see the overall trend, but also the decade, sub-decade variability. And overall, the warming trend amounts to about 3.5 degrees Fahrenheit since 1895. And the 10 warmest years have occurred since 1998. Some of these stats might be slightly different for Vermont, but they're overall very similar or the same. And then projected out to 2100, depending on the projection in the greenhouse gas emission scenario, that ranges from 2 to 10 degrees Fahrenheit. So that's the uncertainty. And as the decades go on, we will see which track that we will follow. Precipitation, an overall increase across the region of about 6 inches since 1895. So that's the annual increase on a given year. In recent years, is about 6 inches more than there was more than a century ago. Obviously, significant year-to-year variability, as we're all well aware of. And heavy precipitation events are becoming more common, as we're all well aware of now. And projected into the future, an overall increase of between 5 and 14% in terms of the annual average accumulation is projected. I'd mentioned 2020 and 2023. Again, this slide is for Maine, but it applies broadly for the region. In 2020, in Maine, not quite so much for Vermont. Vermont was very dry in the growing season for 2020, but in Maine, it was the driest May through September period on record. And 3 years later, 2023, that was either the first or second wettest, depending on how we measure that. I say that because in 1954, this big peak here, much of that signal is due to 2 storms, Hurricanes Carol and Edna, which occurred 10 days apart from one another in August and early September of 1954. And so if we think of just a season that brought a lot of rain throughout the season, that would be 2023. And so these 2 seasonal scale events is a good example of managing seasonal scale extremes only 3 years apart from one another. And I also like to point out that as we've all experienced, beginning about 2016, there were a few years where there was drought variously across the Northeast region, after a decade of overall wet conditions. And so for a few years, people were suddenly faced with having to consider irrigation, to whether or not to invest in that. And then by 2020, that really reinforced the need for irrigation. Then a couple years later, we get one of the wettest summers on record. And so managing this these extremes is a significant challenge. Now, just to have a few words on drought. Historically, short-term drought is common in the Northeast region, and the drought of record in this region occurred in the mid-1960s. That peaked in 1965, and there was a federal drought disaster declaration. But there's also been, in early 2000s, a very impactful drought. And then recently, as you can see in this panel here in 2020, Maine and Massachusetts and parts of New Hampshire were most impacted, but that did also impact Vermont, upstate New York. That in some ways was a short-term drought. That's a drought lasting up to about 6 months, but there was also some signal carryover. So the short-term droughts, again, lasting up to about 6 months, are relatively common in the record in New England. Flash droughts that have sudden onset, it might only last a month or maybe 2 months. Those may become more common. We're not sure yet, but a good example of a recent flash drought was in the fall. And I don't have a graphic for that, but in some parts of the Northeast region, it was the driest fall on record, September through October, and that's true of Maine as well. And so now I'd like to move on to extreme events and also why we're seeing extreme events and more extremes in general. And it links to how warming is intensifying what we call the hydrologic cycle. So that's the transfer of water into the atmosphere through evaporation, where through heating, this moisture circulates through the atmosphere. Eventually, there's cloud formation, precipitation, and there's this overall cycle of water going from the oceans into the atmosphere, and then back onto land through precipitation into lakes and rivers and back out to sea. So in a warmer climate, this process is more vigorous. Kind of like if you have water in a pot and you turn up the burner, the process is more vigorous. There's more convection. It's stronger convection is one way to look at it. And so at the large scale, worldwide, this changes the way the atmosphere circulates. And it has an impact on the jet stream, for example. And also when we think of heavy precipitation events, an important part of this is not just the changes in circulation, but also that warmer air holds more water vapor. And so for a 1.8 degree Fahrenheit warming, or it's 1 degree Celsius, there's approximately a 7% increase in the holding capacity for water. So there's more moisture. On average now, there's more moisture that's available to fall as precipitation. And the Northeast region has seen the largest increase in heavy precipitation events in the United States. And so these are the 2-inch and 3-inch precipitation per day precipitation events. And then also some of the extremes that are beyond the 95th percentile and even beyond the 99th percentile. Here's an example from October of 2022 for Maine, in which here's the 95th percentile of all daily records from the Bangor International Airport, dashed in here. And there was an event that it occurred within about 12-hour period overnight between October 14th and 15th, producing 5 inches of rain. Here's the distribution of that rain across the state. Almost half of it receiving 3 inches or more, some places receiving up to about 5 inches. And then there was road damage, other infrastructure damage, and so those type of events we're seeing more of. And now for Vermont, as all of you on the call from Vermont will know much better than I do, the event from July 10 to 11 in 2023, in which there was a slow moving system of rainfall that encountered a blocking high pressure more to the north and east of us. That caused the storm system to stall. It was not a hurricane, even though this was the worst rainfall and flooding event since 2011 Hurricane Irene, but yet this still produced record or near record total rainfalls, 3 to 9 inches in some places, and severe flooding and huge destruction for the state of Vermont. And in the Q&A afterwards, it'd be interesting to hear some experiences of that event. I've seen photographs, I've spoken to colleagues, and I realized that the state was severely impacted by that, but I'd like to hear personal stories too. Here's another extreme of a different sort that anyone who is in this region may recall from 2012. So I saw it referred to as Summer in March in the press, and I thought that was a good title to keep. In the third week in March, peaking between the 22nd and 23rd, across the region, temperatures into the 80s. At Montpelier, temperature 84 degrees, Bangor 84 degrees, and for most of northern New England, this was by far a record in the earliest 80-degree temperatures that were recorded in the region, and was not a very good snow season in general that year. Now another extreme event that I've already mentioned briefly, the May 18, 2023 freeze event, which had huge impact across the region, especially in Vermont. And this animation shows in blue, those are temperatures below freezing, green above freezing. And then this chart over here is for a weather station in Old Town, Maine, which is a little bit past Bangor, roughly central part of the state, and in which there's a surface temperature probe at that station. And the temperature dropped down to 22 degrees Fahrenheit for about 45 minutes or so. So this was a hard freeze, and a very significant late season event. In central Maine, the next comparable event I've found from station data I've looked at, you have to go back to the 1950s. And so a very an unexpected late season freeze. And a couple articles from Vermont and acknowledging the natural disaster area declaration that was made, releasing funds. Tree fruit orchards, very significant impacts. And again, I'd be interested to hear personal stories of this event. So now moving on to the growing season. I really like showing this chart. And even though this says Maine statewide annual temperature, again, broadly applicable, because it shows that if we consider, if we go back to the statistic I mentioned of over the past little more than a century, there's been a 3.5 degree Fahrenheit warming of mean annual temperature. Some might say, well, that doesn't sound like much. What's 3.5 degrees Fahrenheit? Well, when we look at this chart, we can then start to see how this affects heat accumulation and the relative length of the growing season, the warm season in general, and also the winter season. So as you can see, January through December on the x-axis, and temperature in Fahrenheit on the y-axis. And these three curves here are for three different climatologies. The average for 1901 to 2000 is shown in the blue line. and an average from 2010 to 2023 for more recent climatology in orange, and then a climatology projected centered on 2050. And so if we look at the two historical climatologies, we see that there's overall been about a 2-week lengthening of the growing season. Now, I say growing season here, I'm using a 50-degree Fahrenheit datum. And this is an approximate. That if we, and you'll see in a couple other slides, if we use event-driven first and last frost, that's really what is traditionally used to define the growing season length. But we can also use these monthly data that are smoothed, and then we can just use this as an approximation. And then, so in general, we see that between the century-long climatology in the more recent 2010 to 23, there's been about 2-week lengthening. And also the area beneath these curves, if we were to calculate that area and compare them, that increase, which is on the order of 10, 15% on that order, that's the increase in growing degree days, depending on what baseline we're using as well. We might use a 32-degree baseline for that calculation, or we might use a 40 or 50. But now we can start to see how what may at first appear to be a relatively small increase in mean annual temperature, when we look at the annual cycle, that translates into big changes and big impact on ecosystems and on crops. And if we now briefly look at the winter season, significant warming, as well as an overall reduction as the climate warms, the length of the snow and ice season is shortening. And then, as you may have already read some of these notes on the chart, in the springtime, of course, there's overall decreasing snowpack, earlier snowmelt, and different timing, earlier timing of spring runoff overall, and lake ice out. And then in the fall, later onset of snowfall and lake ice on, and all this has implications for the start of the growing season in spring and the end of the growing season in the fall. Northward shift of plant hardiness zones. These maps utilize the same methodology and color scheme that you will find in the USDA hardiness zone maps. But I used the raw temperature data because I wanted to be able to calculate this for different climate periods. But again, it's the same methodology, which is across this average climatology. So for example here, 1981, 2000, a 20-year period, the extreme minimum temperature at every grid cell, that is what these maps are based on, and what the plant hardiness is based on. And so you can see that between 1981 and 2000, compared to 2001 to 2020, there's this overall northward shift of these zones. And of course, that is based on extreme low temperature. Now, getting into the growing season, though, there's also the component that relates to when temperature is above freezing. And I thought it might be interesting for folks. Many of you will already be familiar with this, but for those who may not be, I thought we could step through this. So the growing season defined by the period between the last spring and first fall frost. Now, the baseline that we use, it varies depending on the plant or the crop, and whether or not we're concerned, whether or not the particular plant or crop is impacted by a light freeze, 29 to 32 degrees Fahrenheit, or moderate freeze, 25 to 28, or severe. And so we can use different definitions depending on the overall purpose. And also to note, frost forms when the air temperature drops below the dew point, and when the dew point temperature is below freezing. It also depends on the humidity at the time, whether or not the air is still, whether or not an inversion forms. Um, but overall, these are the categorizations and the overall approach. So this example is the growing season length in days for a 32 degree Fahrenheit threshold. And as you can see, the overall trend is up. The growing season is getting shorter. Here's the growing season length. Excuse me, I misspoke. The growing season is getting longer, and as shown here. But because of variability, there can be surprises. So in 2020, for example, that ranks among one of the shortest growing seasons on record at caribou for this 32 degree Fahrenheit threshold, comparable to some events from the 60s and 70s. And then the warmest or the longest growing season on record at this particular site was 1998. That was an El Nino year. There was a really strong El Nino that particular year. So now we'll step through and look at a couple of, oh yes. I thought it'd be interesting to show everyone some of the daily data for these individual years and then compare it just so you can see, just to emphasize the event-driven nature of the growing season length versus the overall heat accumulation. So we'll look at 1963, 2020 as the short growing season years, and then 1998 as the long growing season year. We'll see 1998 first. Okay, so 1998, the last frost in the spring, again for the 32 degree baseline or datum, was April 28th, and then the first frost was on October 6th, and so it's 160 days. And now I should step through this chart. There are three sections. Up here is the average temperature anomaly, showing where it's either warmer or cooler than normal for that day of the year. In the middle is the daily observed temperature, shown in black, the minimum and maximum for each day of this selected year, 1998. The red line shows the maximum temperature for that day of the year for the entire record, and the blue line shows the minimum, the record minimum for each day. And then these two lines here are the normal high and normal low for the day. And this blue line, this blue dashed line, that's the 32 Fahrenheit datum. And then precipitation's at the bottom. It's kind of incidental for this particular discussion, but the black lines show the observed precipitation and the green line shows the record for that day of the year. So now we'll jump to 1963. In 1963, the growing season was only 103 days if we use 32 degrees Fahrenheit as the threshold. May 24th to September 5th. Now note up here this temperature anomaly. It's fairly balanced, but overall you can kind of get a sense for that this was a cool year overall. Now let's step through to 2020, which had a comparable growing season length, but you can see there's a lot, the summer was much warmer. But there were these events that produced a late season frost in early June, and then frost returned mid to third week in September. And so even though there was more overall heat, the growing season was still truncated by these weather events. And so that's to highlight that more. These two maps show the cumulative melting degrees, or really growing degree days, for 1963 versus 2020. And you're going to see that indeed it was a much warmer year, 2020. Here's the approximate location of caribou, but the growing season was still truncated because of these weather events. And so it's still important, even though overall the climate's warming, overall the growing season is getting longer. In terms of whether or not you should plant early, or if you can keep growing into the fall later, it still comes down to there is risk, and it's still important to use the long-term climatology and to be mindful of the probabilities for a given date of which a frost is expected. And so now I'd just like to do a quick summary. There's been warming across all seasons that's been observed across this region, most in winter, but also significantly in fall and late summer. Overall increase in annual precipitation, largest increases in summer, and we're seeing more heavy precipitation events, which is shown on this other highlight here. And this is associated with changing weather patterns and more overall moisture in the atmosphere on average. And there's also increased likelihood of blocking patterns in the atmosphere, which can produce heat waves and also cool waves. Growing season length is increasing. It's more degree day accumulation, but again, in terms of risk, there's always risk of an unexpected late frost or early frost. And so we have to be very careful as we plan the season. And still very much have to look at the weather forecasts to see if those are coming. Just some resources. Maine Climate Office website has data visualizations, mostly focused on Maine, but also climate outlook maps. These are from the NOAA Climate Prediction Center, and these update every day, as well as there are monthly and seasonal products on here as well. And I have historical first and last freeze and frost dates, again from NOAA. There's also a link to a really handy utility where you can select individual station data and look at the historical first and last frost, as well as total accumulated precipitation, growing degree days, a lot of other different things that are related to agriculture. So this tool is part of the NOAA Regional Climate Centers, and there's a link to that. And then I'd also like to mention again my colleague Leslie Ann DePigny-Giroux, Vermont State climatologist, as well as anyone on the call who may be from New Hampshire, my colleague Mary Stampone. As state climatologists, we provide climate services, climate and weather data and information. We work with stakeholders across our state. And the three of us happen to be on a couple of projects, so I know them quite well. And please do reach out to them if you have questions. Also, please feel free to reach out to me as well. And my email address is birkel@maine.edu. And thank you very much.
Awesome. Thanks so much, Sean. That was super interesting. And I know we have a bit of time and you haven't had a chance to take any questions yet. So if anyone has a question for Sean, feel free to jump in. We've got a few moments before we get into Joshua's talk.
I got one. Sean, could you share your PowerPoint with the people that are on the call?
Absolutely. I'd be happy to.
Thank you.
Welcome.
I was just curious about, I was thinking about growing season length versus kind of the amount of time in the year you have to, get great photosynthesis, which that doesn't really change, right? Is there anything about temperature that it has an effect there that you know of?
Well, the overall I'm not sure how well I can answer this in terms of, because this is more plant physiology. But overall, the plants will respond to both the photosynthesis, but also the accumulation of heat and the evaporation rate, which is impacted by the heating. I'm wondering if perhaps if anyone else on the call might have a better answer, because I don't want to step too far outside of my area and give incorrect information. but in general, the plants and ecosystems are responding to this increased accumulation of heat, and uh, now how it would be interesting to compare the signal of so in terms of the light received, that would be impacted by cloud cover, and so we could compare how cloud cover is changing during that time, and compare that to the changes in the overall heat accumulation. So very interesting question. I wish I could answer it better, but I hope that helped at least a little bit.
Yeah,
Hey,
no, those are
Sean.
some good thoughts. Thanks.
Sure.
Hey, Sean, thanks for the talk. I just wanted to jump in on the plant physiology
Hi, Allison.
side. Hey, um, yeah, cloud cover definitely will be a primary aspect, but in terms of photo period and sort of day length and overall light angle and intensity, Nick, you're right, that's not shifting because that has to do with our planetary orbit.
Oh, I see another question in the chat. What am I doing differently in my garden? I must admit, my wife has a garden and I help out, but um, I'm more the helping hand. I say, how can I help? And then I do it. And I will say that in 2023, we had a hard time with the cucumbers. There was too much water. Some things just didn't grow, and it was just super muddy. And I know that many people in their home gardens had similar experiences, and I know that many farms and farmers had difficulty accessing fields, and that there was rot from there being too much water. And so I'd be interested to hear from others as well in terms of what you experienced and how you've had to try to manage that.
Sean, there's another question in the chat about the consequences of high dew points in the summer.
Oh, yes, I think the immediate consequence that we all feel is the high overnight low temperatures. And so with a more humid atmosphere, there's less radiational cooling at night. And it's really the daytime lows are increasing more than daytime highs. And so if we were to look at the time series of both, you would see a steeper trend with the lows. And so just warmer mornings, fewer summer mornings that get into the 40s, more and more summer mornings that stay in the low 60s in New England. And now one interesting question becomes, and I don't have an answer for this, but what is the impact on crops? Because this would be the overnight hours. They aren't basking in sunlight, but the temperatures are staying warm, and that must have some impact. I'm sure there's research on this, but I think that's something that could be a factor impact. Ambrose?
Yeah, hi. Thank you. I guess along those lines, that question also reminded me of an experience, and over the last 2 years, I don't work outside full time the way I used to, but my sense was that there was many more times that it felt like there was a lot of humidity in the air, but then rain didn't actually happen, so there was no clearing of that heat. So yeah, it's not a technical question, but maybe you could reflect on that.
Yeah, one thing I've noticed, I think people are really good at capturing the mean over time. If we as any of us who have lived in the same general place their whole lives. I grew up in Bangor. I now live in Orono, just the next town over, and done a lot of traveling, but I've always lived here. And I remember how it was when I was a kid. I wasn't close to the climate data at that time, but um, um, I can tell when we get one of these months, it's it seems really different than it used to. And then when I look at the data, I can see, wow, yeah, it really is. And I forget, I think it was 2022. It was the hottest August. It was the warmest August on record in Maine, with the highest, the most humidity, and it ended up being the highest overnight lows. By mid-month, I could tell. I said, wow, this is going to be some kind of record. I just don't remember August being like this. And then as I talk to audiences and I collect stories, and people will also uh, will say, also, yeah, this is much different from when I was younger, but we just have this we just have this ability to, over time, we can kind of tell what the average is, and we can tell how it is different now sometimes in subtle ways. But and so the increased humidity in summer, I personally have noticed it, and it's shown in the data too. So I think anecdotal information is very important, and it's especially useful when it can be paired with data and we can confirm. And so we're not just looking at numbers, but we can also relate this to our everyday lives and experiences.
Awesome. Thanks so much, Sean. We're going to shift the conversation a little bit and start to draw links between the climate trends that Sean was talking about and the implications and impact that has on soil and how we manage our farms. So I want to turn things over to Joshua Faulkner, who's going to pick up the second part of our presentations tonight.
Thanks, Kevin. And thanks to Sean for a great presentation to kick us off. Let me see, give me just a second here to get my sharing started. Are you looking at the right screen?
I think we can see it, Joshua. Yeah.
Good. Okay, thanks. I got funky things going on my monitors, but okay, I think I can do this. All right. So yeah, thanks again to Sean and for a great presentation. Thanks to MOFGA and NOFA Vermont for hosting. Nice to see so many folks here. So Joshua Faulkner, I'm a research associate professor here at UVM in Extension, and started actually almost exactly 12 years ago when UVM decided that a farming and climate change program would be a really good idea to address some of the issues that farms were facing as a result of climate change. And really that was spurred by Tropical Storm Irene, for those of you who remember that, in 2011. And while it's been a roller coaster since, and I feel like it's, this is almost like deja vu from what farms were experiencing after Irene to what they dealt with after 2023, and then to some extent some parts of the state in 2024. So that's just a little bit of the work I've been doing. Primarily focus on water management within agricultural systems, and that also includes soil management too. And so that's really the lens I take when I think about climate change and impacts on farms. So I'm going to, there's a lot we could really talk about here, but I'm going to focus on three things. I kind of tend to think of these as the top three impacts of extreme precipitation and on agricultural soils and agricultural production in general, really in Vermont. And I assume this translates to Maine, although most of my work is of course here in Vermont. So those are soil erosion, saturated soils, and then soil compaction, which is I think I'll show is very related to these this change in the moisture regime as well. So let's jump in and just start with erosion. So Sean did a good job talking about the degree of extreme events that we're seeing. That's well noted, and that's something that I think is interesting when you work with a lot of different farms, you know, small vegetable farms to large dairies, and everyone agrees on this, right? That the storms are so much more intense than they used to be. It's interesting what Sean said about we're really good at recording means as individuals. I think maybe this is a really good example of that, because farmers talk about this and how difficult it is to manage soils given these types of events. And so this is just a photo from Addison County, Vermont. I live in Addison County, and you can, after any extreme event, you can see me out on the road trying to get some good photos of gullies. I have quite a library of gully erosion photos, and the past couple of summers have really added to that. But this was one from just a couple of years ago. And then I use this photo a lot because this is the first summer I was in Vermont in 2013, and this is after one single thunderstorm. Vern Grubinger took this photo. I'm sure many of you know Vern with UVM. And I'm about 6'3"-ish, and this gully here I'm standing in is up almost to the hip pockets on my jeans. So a pretty substantial amount of soil lost from this, just from one storm. And this is actually sweet corn. This is a large vegetable farm in Chittenden County, Vermont. And I'm grinning, and I shouldn't be grinning, right? This is horrible for the farm. This is their foundation of their production, is this topsoil. But I'm a soil and water engineer by training, and I'd studied, you know, the Dust Bowl and things like that in school, and really had never seen gully erosion like this in an agricultural field until coming to Vermont and starting my work on farming and climate change here. And I use this projection that I have on the top of your screen quite a bit, because I you know, in initial work, this just really struck me and seemed to hold true, that this is from Mark Nearing and colleagues with USDA ARS, where they projected we'd see this increase in annual erosion as we see increases in annual rainfall. And this was done for a corn and soybean system. But I think it's certainly, you know, we have different systems in Vermont and Maine, but I think it should absolutely give us pause about how we manage our soils, given what's happening with rainfall. Okay, so I think where we want to start with kind of trying to deal with erosion is really thinking about something very simple. And that's this kind of water balance or mass balance between infiltration and runoff. And this is I don't think everyone understands this intuitively, but I'll just put it on the screen here so we can just have it written down and kind of agree that it's true. And we'll start with the knowns. And it's the first point is that as runoff increases, the risk of erosion and soil loss increases, right? The more water we have running across our fields, the greater chance of soil loss, right? And so then the second known is that as infiltration decreases, the amount of runoff and therefore the risk of erosion increases. Okay. So this is just like you see in the images at the bottom of the screen. The more water, when it rains, the more water that soaks in, the less water runs off. And the less water that soaks in, the more water runs off. And so therefore, really our goal here to prevent erosion from these extreme events is to try to maximize the amount of rainfall that soaks into our fields. And then that's, again, I don't think that's a revelation for anyone, but I just want to kind of start from that place. And then let's talk about how we achieve this goal of maximizing infiltration. And so infiltration is controlled by a number of things. And some of those are what we call inherent soil properties. And texture is a big one. And so this is just a very simple figure showing that as our soil texture changes, so if we go from the top line on this figure to the bottom line on the figure, our soil is becoming finer textured. So we're moving from a sandy soil to a loamy soil. And if we had clays on this, an even finer soil, we'd see a reduction in infiltration rate even more. So this is all well and good, but these are things we can't change, right? We can't change our soil texture. These are inherent properties. What we can change, though, is how we manage that soil. And this is an old figure, but I think it's fantastic. This is from 1950, but it looks at infiltration depths over a given area, and then it compares just this wide variety of management on the right hand y-axis. And so if you look at the start from the bottom, there's bare ground that's been crusted that has surface sealing that's occurred, and we'll talk more about surface sealing here in a minute. Then just tilled ground, weeds or grains, so things that aren't don't provide a lot of cover. And then we move into our conservation cropping systems, and then our perennial sods or pastures or hays. And you see just the amount of infiltration go up and up and up and up, right? So this is just, these are ways we can manage soil and in which to harness kind of these ideas around and processes related to soil health on improving soil structure and really increasing the amount of water that soaks in. So let's talk a little bit about soil. So soil health is, there's a lot of energy behind that right now. It's a big topic. We could talk about that for hours, but I'm just going to try to simplify it into three basic principles that are with the idea of what we can do to help water soak into our soils, to get more of our rainfall to soak into our soils. And the first one is soil cover. And of course, I'll have a few more slides on each of these, but soil cover is just that. It's pure physical cover, and it can be achieved with mulches and residues, but it can also be achieved with preferably with living cover, like cover crops. Reducing the amount of disturbance that we have in our soil. So once we have a well-structured soil, our soil biology has done its work. It has created soil aggregates, it has created these larger pore spaces in the soil, which are absolutely critical. Not the small pores, but the large pores for infiltrating water. The worst thing we can do then is drag a piece of tillage equipment through that soil to destroy all that structure. There's various ways of reducing our amount of our frequency of disturbance and also our intensity of disturbance. And I think those are like conservation tillage practices, no tillage practices. There's lots of different ways of doing that. And then the third one is really building organic matter. And this is key, because the organic matter is really the energy that the soil biology harnesses in order to create the soil structure, to build the soil aggregates in the first place. So the more fuel we can give to soil biology, the more the better chance we have of improving that soil structure and then soaking more of the rainfall into the soil. We can build organic matter with lots of different ways. Again, cover crops are great, organic fertility sources, thinking manure and compost, and then crop rotations are also helpful there. Okay, so let's jump into each of these just a little bit more and show you some data and a little bit more support material for each of these. So when raindrops hit the ground, they hit the ground at a terminal velocity of about 32 feet per second. When they do that, if you think about a soil aggregate, it's kind of a crumb size particle. When raindrops hit that at 32 feet per second, if that aggregate isn't stable, if it's weakly aggregated, it blows apart in all its little constituent sand, silt, and clay particles. And it kind of destroys that structure, right? And when those particles settle back onto the surface of the soil, they're small enough that they fill in the small pores on the soil surface. And when that happens, that surface sealing occurs, or surface crusting. And when that happens, we're in a really bad place, because when the surface becomes sealed, no additional rainfall soaks into the soil. Everything runs off. And that's when we start to see these are very erosive events occurring. Some of you may have experienced this yourself in a garden or in a farm field, in a really dry summer. You think, God, we really need some rain. We really need some rain. And you get this half-inch, 3/4-inch storm in the afternoon, and you walk out there and you kick back the soil, and it's, lo and behold, it's only wet down about a 3/8 of an inch, a half-inch on the surface, and then dry as a bone underneath. That's surface sealing. And that's when aggregates have essentially been destroyed, and all additional rainfall runs off. We've created a parking lot when that occurs. There's lots of, so soil cover prevents that, right? It just literally prevents those raindrops from physically damaging our soil aggregates to start that process of runoff and erosion. There's lots of data to support that. This is just one study, very simple study, where they looked at the degree of soil cover as we increase that soil cover, how that affects runoff and infiltration. We see runoff quickly decreasing with increased soil cover, and then infiltration increasing. So again, it's that mass balance, right? We see less runoff and more infiltration, and vice versa. A tool that I used in a previous position, I had a rainfall simulator. I'm guessing some of you may have seen one of these. NRCS and some other conservation districts have these tools, and they take them around. They're really cool. You take samples of soils wherever on a farm you want to do a workshop or demonstration. You put them in these trays on this table. And the trays have a bunch of holes in the bottom of them. So if water soaks into the soil, it'll run through the tray. And the water that runs through the tray is captured in the bucket in the back. You can kind of see a line of buckets in the front and a line of buckets in the back. That's the line of the buckets in the back. That's the infiltrated water. And then the line of buckets in the front, that's capturing what runs off of these soils, right? So I'm just going to talk about the two soil samples on the left. These were taken side by side in a cornfield, conventionally tilled cornfield. And one, I just simply put some straw mulch on top of it. That's the only thing that happened. And then we rained on them. What you can't see in this photo, there's a rainfall sprinkler head above the frame, above the photo frame, and it rains pretty intensely on these soil slices. And then so we did that, and then you see what happened. I mean, the proof is literally in the pudding here. You look at the jars for runoff, and that soil that had no soil cover, had no physical cover on it, is just full of water because surface sealing occurred, and lots of soil particles, and of course nutrients as well. And the bucket on the right has very little, maybe an inch of water in the bottom of that bucket of runoff water, and that water is relatively clear, much less turbid. And then you look at the back bucket, and again, there's your proof, there's your mass balance, right? The whatever ran off could not soak in, and whatever soaked in could not run off. So you kind of see this happening. This is what, at this like really cool tabletop scale, this is what happens at a landscape scale. And you can imagine how much erosion would occur in gully formation if we had an extreme event on an entire field. Okay, so that's soil cover. So reduced disturbance. I just want to show some data how this influences soil loss and water loss as well. Here's a figure on your right-hand side of your screen from Kentucky, from a study in Kentucky where they looked at conventional till, no-till, and then a no-till with a double crop. So we have again, reduced disturbance, but we also have a soil cover and increased organic matter. And you can see just from moving from conventional till to no-till, so reducing the amount of disturbance, maintaining structure, maintaining soil pore, macropores, we see water loss drop off, and we see soil loss or erosion steeply decline. So there's lots of ways, like I said, there's lots of ways of doing this. Very difficult I will admit, this is a NOFA and a MOFCA crowd, very difficult to do in organic vegetable systems. People are experimenting with it. It's very exciting to see them find new ways and kind of start to make some change around the edges here. And then the last one is that increased organic matter. And this is a figure from a study on tomato in tomato production. And I believe this was performed in California, I believe, where what they did, they managed several plots in the same way, except for the fertility source. And in the plot on the bottom, they used the synthetic fertility source for their fertilizer. And then the two on top, they used organic fertility sources. And I can't remember if it was a manure or a compost or composted manure. But just from that difference in the type of fertility source, they saw a significant difference in infiltration of rainfall during a simulated rainfall experiment. And that's because the soil biology had the organic matter there to build the structure to create the macropores to soak in the water. All right. So that was erosion. Now I'm going to check my time here real quick. I think we're doing okay. I want to talk about saturation. That was number 2. And so here's a photo of Sean mentioned the kind of really just train wreck of a summer we had in 2023. This is a cornfield in Addison County, Vermont, where I do a lot of my research. This is a greenhouse gas emissions plot. You can see the pipe ring there, or chamber in the lower right-hand corner of the screen. This field was saturated like this for at least a month, if not almost 2 months. We had saturated areas within this cornfield. This was August. The floods came in July 11th, and we had at this part of Vermont, we saw. I measured on my rainfall stations 23 inches of rainfall for July and August. The official NOAA data says it's closer to 16, but even 16 was the highest rainfall on record for those 2 months, stretching all the way back to 1895. And then again in 2024, we didn't see this this flooding near as widespread, but where we did see flooding, it was extremely damaging. This is Joe's Brook Farm in Barnett, Vermont. St. Johnsbury with this storm at the Fairbanks Museum Observatory recorded over 8 inches of rainfall in a 24-hour period, which was shattered the prior record, of which was, I think, just under 5 inches. And so this is another example of saturation we saw. And this saturation is actually coming from a flooded river, where the image from 2023 is just waterlogging of soils within a field. So this is what we're facing, right? And so how do we deal with this saturation? So we'll start with nutrients. We'll start with some of the effects, and then we'll spend the bulk of our time here talking about how do we manage this saturation, because I think that's the important bit here we want to take away. So we'll start with nitrogen. So saturation effects on nitrogen. This is a very simplified nitrogen cycle in a cropping system. If we start from the left, we add our fertilizers, our manures, or compost, whatever it is. There is some natural sources of nitrogen in rain and snow, atmospheric deposition. And those become mineralized within the soil, or they get added as ammonium or nitrate. If it's ammonium, it will then go through the process of nitrification within the soil and be converted to nitrate, which is on the far right-hand side of your screen, the NO3, that's nitrate. That is the form of nitrogen which we see loss occurring. And that can occur in 2 different ways that are very related to heavy rainfall. The first way is up through the surface of the soil, and that's denitrification. So that's when we have very saturated soils, very low oxygen. We see nitrous oxide being produced or dinitrogen being produced, and losing that nitrogen literally up into the air when we have saturated soils. The other way we lose nitrogen through when we have heavy rainfall is through leaching, and this probably dominates, especially in coarse soils. Nitrate is negatively charged. You see the little negative sign there, and so it doesn't bind tightly to soil particles. It's really slippery, and it moves readily with water downward. So we can see significant amounts of nitrate leaching when we have heavy rainfall. And not in 2023 or 24, but in some prior years, I've done some monitoring on agricultural fields and seen anywhere from 70 to up to 100 pounds per acre of nitrate being leached from the soil, believe it or not. So, and that's not that uncommon if you look at the literature and in some other places, especially where higher rates of nitrogen are being applied in coarser soils. There's this slide has a couple different things happening here. One is that this provides some guidance for how we should manage to prevent nitrogen leaching from an environmental perspective. We want to avoid losing that nitrogen into our waterways. But then what I've kind of circled or put in a red box here at the bottom is how we deal with nitrogen, or how we handle saturation and losses of nitrogen to that denitrification pathway or that leaching pathway. And so I'll kind of quickly step through the upper bullets. If we want to minimize leaching, we first need to kind of change the way we manage nitrogen on vulnerable soils. Those are our sandy, well-drained soils, or tiled soils, or drained soils. We minimize the amount of residual nitrogen we have in that soil going into the winter time. We scavenge residual nitrogen with cover crops, soak it up so it can't be leached, and then change the way we manage our irrigation. If we over apply water, the same way as if we have heavy rainfall, if we over apply irrigation water, we're going to leach nitrogen. And then finally there, how do we manage nitrogen post saturation? Chances are we've lost a lot of nitrogen, if not all of our nitrogen, when we do have saturation. The best recommendation there is to evaluate our soils, do a PSNT or a pre-sidrous nitrate test. And I know it's not necessarily that we're going to sidress anything that was saturated, but this test will help us understand how much nitrogen is in the inorganic form in that soil that can be taken up by plants. And if we need to add more nitrogen, how much nitrogen did we lose after that saturation event? The other kind of nutrient related effect that we see from saturation is a follow-on effect of what's called flooded soil syndrome. And I would encourage you to Google this and check this out. There's a lot of information on this from the Midwest. And there's obviously effects on yield, acute impacts on yield from soil saturation, but this is something that lasts much longer. So when we see flooded soil syndrome, that's from when we have these extended periods of saturation. Those actually not only impact the crops or the plants in the ground, they impact some of the soil biology, and primarily the AMF, the arbuscular mycorrhizae fungi, which help plants acquire nutrients from the soil. They kind of have a symbiotic relationship where the plant helps the AMF get water, and the AMF helps the plant get nutrients, and primarily phosphorus, and to some extent zinc. So this flooded soil syndrome, you can see phosphorus deficiencies if you've had extended saturation occurring. And really the best recommendation, if that is happening, is to establish some sort of crop, get some living roots in the ground as quickly as possible, and try to rebuild that biology. Okay, so how do we avoid saturation? And really the obvious answer is drainage. And drainage is not new. I love to use this slide. You know, it's been wet in Vermont, but it has perhaps always been wet in Vermont, or we've always had wet years. This is from the 1912 annual report of the Vermont Ag Experiment Station. And so it's just a good reminder that farmers have been dealing with wet conditions. This is New England for a long, long time. So what are our options when it comes to drainage? And I'm just going to talk about two today. There are some other other ways, but these are the big two that I see being used and most applicable to Vermont farms. So the first is an interceptor drain. And this is put simply kind of a French, most people would think of this as and call it a French drain. This is a gravel filled trench that has a perforated pipe in the bottom of it. But the trick here is the placement of that trench, the placement of that drain. And they're most effective at the toes of slopes that are adjacent to a production area. And we have certain soils in Vermont that are, I think I have a slide on this a little bit later, that these work really, really well in because of their subsurface flow patterns. But these are simply meant to intercept water that is either flowing on the surface or the subsurface on an adjacent hillside. Could be a hayfield, could be a woodlot, and catching that before it enters the vegetable beds at the bottom of the hill and diverting it. And you can do this with this French drain. You can also do it with surface ditches. I've just shown a couple examples here, but these can be incredibly effective and have a lot of bang for the buck. The other way of draining, which is gaining popularity in Vermont, at least in the 12 years that I've been here, is tile drainage. And we say tile drainage because this used to be literally tile pipes put in the ground, buried about say 3 to 3.5 feet beneath the bulk of the root zone to move water out of the root zone and lower the water table. These are not, we think of this as kind of being a new practice. It's really quite old. It's been around in America for since the early mid 1800s, but the way it's done now is changing in the intensity at which it's being done. There's lots of work that's done on showing the benefit of tile drainage. It improves crop production. It reduces that year-to-year variability. It allows earlier and later field operations, and in some cases, so it improves trafficability. And in some cases, that can almost have as big a benefit to the farm if you can get in the field and do what you need to do when you need to do it, as the primary effect of just draining the water table and avoiding saturated root systems. I have some data from field crop systems. I'll let you look at that. I don't need to walk through that. It's interesting that I do see a lot of farmers interested in tile drainage, and traditionally it has been used in field cropping systems, but I think probably over half the farmers that I talk to now who call and are interested in this are really those growing vegetables and to some extent fruits. So this is, and that makes a lot of sense given the high value of vegetable crops and fruit crops. So this is not just for our field croppers. This is across ag sectors. So a lot of people ask, is drainage? I'm a little bit worried about installing something like tile drainage. It will remove water that plants could potentially use during these. I think Sean called them flash droughts. Really, that's fascinating to learn more about that. And that's really not the case. Crops, tile drains remove free water or gravity, water that can be removed via gravity. And a good analogy for this is if you think of a sponge that you soak in a bucket of water and you pick that sponge up out of the water, there's going to be some water that drains from that sponge before you squeeze it. That's the free water. That's water that can be removed by gravity. And then it's really the plant's root action that removes the rest of the water. And so that would be you squeezing the sponge So that's plant available water left in the sponge after you let it free drain. So tile is not removing that. It's not squeezing that sponge, if you will. And drainage works in wet years and it works in dry years. It has, that's kind of a little counterintuitive. Of course, we know it would work in a wet year based on the data, but it actually keeps the water table low in a dry year in the spring, so that roots can go deeper. Where if there was no tile, those roots would not go deeper, and so that plant would suffer. That crop would suffer later on when we do have drier conditions in August, for example. So this works in both wet years and dry years. And then I think one of my last slides on drainage, the importance of understanding the soils on your farm can't be overstated. Texture affects a lot of the design parameters around some of these drainage interventions. If it's a clay, if it's a shrink swell soil, if it's a sandy soil, if it has certain layers within it. A great example of that is this kind of fragipan layer that we see in a lot of soils in hilly parts of Vermont. And this is a virtually impermeable layer, about 20 to 30 inches below the ground. And so water perches on this. And if this is very important to understand if you're going to install one of those interceptor drains that I mentioned earlier. Also good to know that you don't want to put tile drains in this dense layer, because they will kind of encase that tile and prevent water from entering it. So just good to understand the soils and work with someone who does. And then you can't talk about drainage without talking about the environmental concerns. This is where I do a lot of research and monitoring on nutrient loss through tile systems. It's well known that nitrogen moves readily. Like we said, nitrogen leaches readily. It moves because of that, it does move into tile systems, and we can lose a lot of nitrogen because of that. And we've also seen phosphorus moving through tile drains, and there's new rules that the Agency of Agriculture in Vermont has implemented because of that. But the net effect on phosphorus loss is not yet known. So, if we think about that mass balance again, if we have drained soils, we're going to see less runoff, less surface runoff. So even though if we're seeing phosphorus in tile drainage outflow, is it more total phosphorus than if a field was undrained during these extreme events and we see more surface erosion? So really interesting questions that are yet unanswered. Okay, and then finally, I can finish up here in just a few slides, is compaction. And soil compaction is a very challenging thing, especially in the Lake Champlain Basin of Vermont, because of our heavy soils or clay soils, which compact very easily. So soil compaction essentially is, if you think of soil, it's really only about half of that soil volume is solid material. The other half of it is pore space, and that pore space can be filled with air or water or soil biology, all of which are critical for crop, for healthy soils and for crop production. So when we compact a soil, we're essentially reducing those voids, reducing the volume of the soil that is empty or can hold water and air. And then where this links to climate change is that soil compaction can be exacerbated by moist conditions. So when we have years where we have a really wet spring and farmers are trying to plant, they're getting equipment into the field, perhaps when they shouldn't, or when it's risky. I don't want to say you shouldn't, but when it's risky, because the wetter the soil is, the more likely it will compact. And this is just a classic kind of ag engineering figure from University of Missouri that shows the pressures beneath a tractor tire and how they travel through a soil as it's wetter, as the more so that the wetter it is. And then compaction also affects infiltration, as you might imagine. And this is just a very simple figure. It's showing that as we have a more compacted soil, we see decreased infiltration and of course then increased runoff. And compaction also certainly affects yield. And there's been a lot of work done on this in field crops, and unfortunately don't have any data on this from vegetable crops, but you can see why it would affect yield on the left when you look at corn roots in a compacted soil versus an uncompacted soil. Dealing with compaction, by all means, try to prevent it if possible. Try to avoid getting heavy equipment on moist soils. If you do have compacted soils, biological approaches can be effective in some situations. With deep-rooted cover crops, we've done some work on that, and we've seen some success with sorghum Sudan grass in perennial forage systems. But there are instances where mechanical approaches may be needed. And I'm thinking of deep compaction and really onerous compaction that's formed over, in some cases, decades of tillage. So plow pans, for example. So you may want to do some mechanical work on that soil with some deep tillage, but then it's very important that you account for soil moisture status when you do that. If you go in and do that when soils are moist, you won't really break up that compaction. You'll just slice through the soil. You want that soil to be dry so that you fracture the soil and break it up again, so that water can once again flow through it. All right, and that's I'm going to stop there, and hopefully we have at least a little time for questions.
We definitely do. Yeah. Thanks, Joshua. That was awesome. And yeah, we just want to open it up for questions from the group. While we're doing questions, Meg is going to share out a quick eval for the forum. So please fill it out, but I'll turn it over to folks to ask questions of both Joshua